Welcome to G Fun Facts Online. Today, we're looking at a technology that sounds like it's straight out of a fantasy novel, but is very real and is being used on the front lines of a global battle. We're talking about dragon eggs. These aren't tools to put out fires, they're tools to start them. Deployed by high-tech drones, these small spheres are a key part of a sophisticated strategy to control the spread of modern megafires by fighting fire, with more strategically placed fire. So how do you fight a raging inferno by creating more flames? Let's dive into the unseen arsenal of aerial firefighting. At the heart of a dragon egg is a marvel of applied chemistry. The sphere itself is about the size of a ping-pong ball, made of a high-impact polystyrene shell. Inside that shell is a vibrant purple crystalline solid, potassium permanganate. This chemical is a powerful oxidizing agent, which means it's very good at donating oxygen and making things react. But on its own, it's quite stable. The magic begins when it's mixed with the second ingredient, ethylene glycol, a chemical most of us know as the primary component in car antifreeze. The moment these two substances meet, a powerful reaction kicks off. The potassium permanganate oxidizes the ethylene glycol, creating a huge amount of heat. This is what we call an exothermic reaction. The mixture smokes, bubbles, and after a short, predictable delay, it bursts into a flame hot enough to ignite the forest floor. The final byproducts are simply carbon dioxide, water, and manganese oxide, a harmless, naturally occurring mineral. Now, for aerial firefighting, the most critical part of this reaction is the delay. You can't have the sphere igniting the second it's injected with glycol on the drone. It needs to be dropped, fall through the canopy, and settle on the ground first. This delay, typically between 20 and 60 seconds, is meticulously engineered. It's controlled by the particle size of the potassium permanganate. Finer powders react faster, and by mixing a special slowing additive into the powder. In fact, a safety bulletin in 2023 noted that a batch of dragon eggs was accidentally manufactured without this additive, causing dangerously fast reactions of less than 10 seconds. The spheres were essentially exploding or rocketing through the air, highlighting just how crucial this controlled delay is for safety and effectiveness. The idea of starting fires from the air isn't new. It's been a part of wildland fire management for over 50 years. Used for two main reasons. First, for prescribed burns, which are controlled fires set to reduce fuel loads and prevent future megafires. Second, for backburning, a tactical move where firefighters burn the fuel between a wildfire and a control line, like a road, to stop the main fire in its tracks. The earliest versions in the 1960s were literally aerial drip torches, giant canisters slung under a helicopter, dripping a stream of flaming fuel. The first major leap forward was the helicopter-mounted plastic sphere dispenser, or PSD, often nicknamed the ping-pong ball machine. One famous model is the Red Dragon. An operator inside the helicopter would run the machine, which injects each sphere with glycol and drops it out the door at a rate of up to 130 spheres per minute. This was a game changer, but helicopters have major drawbacks. They are incredibly expensive to operate, require highly trained pilots and crew, and most importantly, they can't fly safely at night or in dense smoke. This is where the drone revolution begins. Researchers at the University of Nebraska-Lincoln pioneered a drone-based system, which led to a company called Drone Amplified, and their flagship product, the Ignis system. They essentially miniaturized the helicopter technology into a sophisticated payload that could be mounted on a powerful commercial drone. The Ignis system represents a quantum leap in aerial ignition. It combines a hopper that holds up to 450 spheres with a mechanism that punctures and injects each one before dropping it. The entire operation is controlled by a pilot on the ground, who can be miles away from the danger. The workhorse drone carrying this system is often the Freefly Alta X. This is a heavy-lifting, American-made drone that can carry a payload of up to 35 pounds. With a typical 20-pound payload, it can fly for over 20 minutes, which is plenty of time to execute a burn pattern. It's built to operate in extreme temperatures, from -20 to over 50 degrees Celsius, and its powerful motors make it stable in the turbulent air found near wildfires. The brain of the operation is the Ignis II dispenser. It weighs just over 9 pounds fully loaded and can drop up to 120 spheres per minute. A single operator can reload the dispenser on the ground in just 2 to 5 minutes, meaning the drone can get back in the air very quickly. But the real magic is in the software. The system is controlled by a custom app on a tablet. Before a mission, fire managers can draw a digital boundary, a geofence, on a map. The system is programmed to only drop spheres inside that area, preventing any accidental ignitions outside the control zone. They can also create fully autonomous flight paths, telling the drone to fly specific lines and drop spheres at a perfectly set spacing. The operator gets a live video feed, often with both visual and thermal cameras, allowing them to see through smoke, monitor fire behavior in real time, and make adjustments on the fly. This gives the firing boss on the ground a level of precision and control that was simply impossible from inside a noisy, vibrating helicopter. Of course, getting these dragon eggs from the factory to the fire line is a complex logistical process. Because they contain potassium permanganate, the spheres are classified as a hazardous material. They have to be stored in controlled environments, away from moisture and fuels. And quality control is paramount. Before any mission, crews on the fire line conduct a bench test. They take a few spheres from the box they plan to use, inject them, and time the reaction. This verifies the ignition delay is correct for that specific batch, allowing them to adjust flight altitude to ensure the sphere ignites on the ground, not in the air. So what is the real-world impact of this technology? First and foremost, safety. Aerial ignition is one of the most dangerous jobs in firefighting. Drones remove pilots and ground crews from those high-risk environments entirely. The pilot operates from a safe location, miles away from the flames. The economic benefits are also staggering. A USDA Forest Service briefing found that using a drone for a prescribed burn costs about $1,800 per day. To do the same job with a helicopter costs around $16,000 per day. That's a nearly 90% reduction in cost. This means land managers can afford to conduct more prescribed burns, treating more acres, and making our landscapes more resilient to catastrophic fire. Drones are also more effective. They can operate 24/7, including at night and in heavy smoke when helicopters are grounded. This allows crews to burn during more favorable weather conditions, like the higher humidity overnight, which leads to more controlled and effective outcomes. During the massive 2021 Dixie Fire in California, a drone was used to conduct a burnout operation down a steep, inaccessible gully. First, its thermal camera provided crucial intel, and then it dropped dragon eggs to create a control line in an area that was far too dangerous for ground crews to enter. Despite its promise, the technology faces hurdles. The biggest is aviation regulations. During a wildfire, the FAA establishes a temporary flight restriction, or TFR, which is a no-fly zone. The rule fire agencies push is simple. If you fly, we can't. An unauthorized private drone in the area can force the grounding of all firefighting aircraft out of fear of a mid-air collision. Official drone operations are tightly controlled and coordinated with all other aircraft in the sky. And what about the environmental impact? The main byproduct, manganese oxide, is a naturally occurring mineral. While high concentrations of manganese dust can be harmful to humans, the amount deposited during a burn is spread over a large area. The scientific consensus is that the risk from these small amounts is far outweighed by the ecological benefit of preventing a high-intensity megafire, which can sterilize soil and cause far greater, long-lasting damage. The future of this technology is even more exciting. Researchers are developing systems that use swarms of drones to autonomously ignite, monitor, and even suppress a fire. Imagine AI-powered drones analyzing thermal data in real time, predicting fire spread, and adjusting ignition patterns on the fly, all without direct human intervention. The Dragon Egg, a device born from a simple but powerful chemical reaction, has armed firefighters with a revolutionary capability. By fighting fire with fire, from a safe distance, and with incredible precision, this unseen arsenal is helping to restore balance to our landscapes and protect our communities from the growing threat of wildfire. Thanks for tuning in to Fun Facts Online.